rest of these homeworks should be coming. I don't know how far we'll get here. Hopefully we'll get far enough that I can hand the homework out and you can get started on it, at least do half of it by Wednesday. And we'll do something similar to what we did today. We will finish chapter 12 and then you'll finish the homework. All right, so the exam is going to be over 10, 11, and this chapter that we're beginning right now, chapter 12, alcohols. So far in chapter 11, 10 and 11, you've looked at predominantly carbon and hydrogen. And then we've looked at halogens. And we just dipped our toes into chapter 12 by the hydration of an alkene, which produces an alcohol. Alcohols are going to introduce the third element, oxygen. Now you can see what you're going to see here is you start putting oxygen on carbons. There's a lot of variety that comes in. Alcohols, aldehydes, ketones, carboxylic acids, esters, ethers, all have to do with alcohol, with oxygen. All right, so in chapter 12, we'll look at alcohols and ethers. All right, so in models, we would use a red bead, a red ball to represent the oxygen. Oxygen has only two bonds to it. H2O, there's a hydrogen, and then there's another bond. This is an OH group. General formula, ROH is alcohols. So we're going to look at alcohols, phenols, the aromatic alcohol, and ethers. But let's just concentrate on alcohols right now. Okay. Chapter 10, 11, we said alkanes and alkenes were non-polar molecules. We did not say that all organic molecules are non-polar. That would have been wrong because alcohols are polar. Now let's pretend, what do we want to pretend here? That we got two containers right here. Let's see if I can make this a little bigger. Here on the left, we have a container full of pure alcohol. So there's a carbon. It could be 1 carbon, 2, 3, 10, whatever, carbon, and an OH group on it. The thing that creates the polar nature of alcohols is this hydrogen-oxygen bond, which is polar. If you remember in 1305, you learned that H2O molecule is a polar molecule. This end of the bond is negative. The oxygen around the oxygen has got a partial negative charge because the electrons are spending more time around there, and the hydrogen nucleus is hanging out here without any electron around it a lot of the times, and so it looks positive. And so that is a polar bond. It's got a negative end and a positive end. This is a polar bond. It's got a negative end and a positive end. Well, if you take one of those hydrogens off there and put a carbon, it still means that that HO bond is polar. All right, so what is this going to... So here's the alcohol. The hydrogen on the OH is attracted to the oxygen on another alcohol molecule. The oxygen is attracted to that hydrogen. This is hydrogen bonding. Hydrogen bonding. It is not a covalent bond. It's not a bona fide sharing of electrons. It's an attraction of different ends of that bond oppositely charged ends of that bond that are attracted to the other molecule. It's a weaker bond than this, but it is a very important bond, hydrogen bonding. Now what we got on the other side, just think of this as another container over here. So we got two containers. Here we've got an alcohol and water. So we throw water into the alcohol. What do we find? Oh, water is made up of OH polar bonds, and the same thing happens. The oxygen on the water is hydrogen bonded to a hydrogen on the alcohol. The hydrogen that is on the OH. And the hydrogen on the water is attracted to the oxygen on another alcohol. You get all this hydrogen bonding, which means that polar alcohols are soluble in polar solvents like water. So a mixed drink of water and alcohol is a mixed drink. It's a solution. The alcohol is dissolved in there. It's not floating on the top. It dissolves in there. You can't make a mixed drink out of propane or pentane or hexane. It will float. You wouldn't want to drink it anyway. What's the consequence of this? It has an impact on the properties. You'll see me making comparisons like this right along through here as we go from alcohols to aldehydes and ketones and carboxylic acids. We're gonna say, okay, this is soluble in water. There's hydrogen bonding. How strong is the hydrogen bonding? Let's look at boiling points. So here's your first example of it. Here is propane, 3 carbons, hydrocarbon, non-polar molecule. So propane doesn't have much attraction for other propane molecules. They're non-polar. They don't hydrogen bond with each other. So propane will boil at minus 42 degrees centigrade. So that means that at minus 40 degrees centigrade, it's a gas. It's already turned into a gas. Now let's take something that's about the same molecular weight as propane, ethanol. This is the alcohol that's in alcoholic beverages. It's got an OH. It does hydrogen bond. This alcohol will hydrogen bond with itself. And look at that attraction of the molecules to themselves means that you have to raise this thing minus 42 up to plus 78. That's a difference of what, 120 degrees centigrade or so. 120 degrees centigrade higher temperature to get this thing to boil. Why? Because it's like Velcro. It's attracted to itself. So you have got to heat it up really hot to break these bonds, this hydrogen bonding, to overcome that attraction and get the molecule to escape into the atmosphere, into the air around it. Okay? So what I'm saying here is at boiling point, when you compare molecules of similar molecular weights, you can look at boiling points and say something about the attractiveness of those molecules to themselves. You can skip this one in the middle. That one's an ether. We'll get to that later. But this key one here, a hydrocarbon with an alcohol. Hydrogen bonding, no hydrogen bonding. This is what's making the difference. It impacts water solubility, soluble in water, and it impacts boiling point. Okay, let's take this understanding a little bit further. let's just compare this one with this one. I'm going to compare this molecule with this molecule. They're both alcohols. 2 carbons and 1 OH. 1, 2, 3, 4 carbons and 1 OH. I just said alcohols are soluble in water. How soluble? It depends. What does it depend on? Depends on how long this chain is. This is the alcohol in alcoholic beverages. It is very soluble. We'd say miscible. You can dissolve, 50, 70, 80% alcohol in water. It's going to dissolve in there. Any mixture of water and alcohol will be soluble. It will form a solution. It's very soluble. Now, we extend that to 4 carbons long, and it is soluble, but not very soluble. 7 grams of that alcohol per 100 milliliters of water.
So the less carbons, the more soluble?
Yeah, or the more carbons, the less soluble it is. And here's a graph. Let's look at this graph. Where's the graph? Here's the graph. So let's look at what we're looking at here. This is number of carbons. So this would be, 1 carbon, 2 carbons, 3 carbons, 4 carbons. 2 carbons is ethanol. Here's the 4 carbons that was just on that previous slide. Butanol. It said about 7. Here it's looking around 8 grams per 100 milliliters. Pentanol. Now we've got to 5 carbons. And we're down to 2 grams. The solubility is decreasing as the chain length is increasing. Okay? As the chain gets longer, the solubility in water decreases. This line right here is alkanes. So this is methane, pentane, propane, butane, pentane, hexane, heptane. So by the time you get up to 7 carbons long, even with an OH group on it, it is no more soluble in water than an alkane. And why? Well, let's look at this. 3, 4, 5, 6, 7. There's 7 carbons long. There's your 1 heptanol. I said, let me draw this one a little bit differently. Let me draw it like this. There's our hydroxyl group. And I said this is polar. This thing little here, this part of the molecule, that OH bond, is polar. That's what is attracted to water. Well, what is that? This whole thing right here is non-polar. So the non-polar component of this molecule is now so big that it's overpowering the little bit of polarity the polarity you're getting out of one OH group. Does that make sense? All right. So this isn't polar enough to make this big, huge molecule attracted to the water and get into the water. So that's this molecule right here. This is 1 heptanol. And we would say it is not soluble in water. A little pinch. About 0.2 of a gram per 100 milliliters of water. So it's just very slightly soluble in water, or insoluble. The OH is always polar. It's just not polar enough to get that to dissolve in the water. Now, if we put more OHs on this molecule, it will increase its solubility. So if I just, here's 7, There's 4, 5, 6, 7. If I put an OH here, if I put an OH here, and I put another OH right here, even though I've got a long chain, 7 carbons long, I now have 3 OHs for those 7 carbons. This will be pretty soluble in water. Because this is polar, that's polar, that's polar. Now you got enough polarity coming into this molecule to overcome the non-polar nature of these carbons. So this will be soluble, and this is insoluble in water. Okay, that's kind of properties. That comes under the heading of what are the properties of alcohols. Now, let's start talking about the nomenclature. How do you name alcohols? You get the longest chain. We're going to pick up that alcohol, OL. That is going to be the suffix on the end of the name to let us know that we're talking about an alcohol. 1-propanol, 2-butanol, etc. So we're going to drop the E of the name of the alkane. We're going to count the longest chain, 6 carbons long. It's going to be hexane. We're going to drop the E, add OL. It'll be hexanol. And then we have to number the chain from the end, putting the OH, giving the OH the lowest number, and then prefix the name with a number to say where that OL is. An OL is an OH group. Where is it? It can be in propanol, it can be on the first carbon or the second carbon. Butanol, it can be on the first carbon or the second carbon. Cyclohexanol, cyclic alcohols, we might not need a number because we just assume wherever that OH is on there. So let's name a couple things. Here's, okay, longest chain. 1, 2, 3, 4. And notice, you say, well, we got a methyl group here, 1, 2. No, this takes precedent. This is going to end up in the name. We're going to call this butanol. So we want to start counting from the end that gets us there with the lowest number. So that is 2-butanol, and it has a methyl group on carbon number 3. 1, 2, 3. So it's 3-methyl, 2-butanol. Okay, here's a cyclical one. Right, without the methyl on it, it's cyclohexanol. We're going to fix the carbon that OH is on as carbon number 1 and count over to the substituent the shortest distance. So we're not going to go 1, 2, 3, 4, 5. We're going to go 1, 2, 3. So it's 3-methyl cyclohexanol. And you don't really have to say 1-cyclohexanol in this particular case, because we would put that on there. Let's just draw that. Let's pretend we can't see it. If you're going to draw it, this is what you would draw first, the parent name. Cyclohexane, cyclohexanol, and then it says it's 3-methyl. So This tells you that's 1, 2, 3.
If you had a double bond, would the OH still be carbon number 1, or would you do the double bond as carbon?
Boy, that's a really good question. So there what you're saying, and your name is Heather. What Heather's saying is, what if we had both the double bond and the OH? We would, let's do that. Let's just make it, we just have a double bond and an OH. We would get to this in a minute. We don't have a way of handling a double bond as a substituent. Okay, so I would call this cyclohexene. So it's cyclohexene with that substituent on it. Let's see, we gotta, this is gonna be carbon number 1, 2. We gotta pass through the double bond. 1, 2, 3. So we will call this a hydroxyl group. You see the YL for a substituent. So this would be 3-hydroxyl cyclohexene. I mean, that's a really good question, because all of a sudden, man, you're telling me if I got an OH, I'm going to call an alcohol. This is an alcohol, but it is an alcohol that has a double bond in the molecule. So it's going to be an ene, cyclohexene, and I can handle that OH group as a substituent.
So you would give priority to the double bond?
Yeah, because I'm giving priority to it. I don't, if I decided to call this cyclohexanol, then what do I do with the ene? I don't have a name for a double bond as a substituent, okay? And double bonds never really are substituents. They're not hanging off of the molecule somewhere. They are an integral part of it. So yeah, you would give precedence to the double bond in the parent name. All right, yeah, that was, and this comes up here later. Okay, here's some 3x5 cards. These are critical, common named molecules here. Tertiary butyl alcohol. Tertiary butyl. That if I just covered up that OH group, that's a tertiary butyl substituent. Well, now we got an OH on it. It's T-butyl alcohol, or tertiary butyl alcohol. That is an isopropyl substituent, and we got an OH on it. It's isopropyl alcohol. Okay, write down the names, the IUPAC names of those two molecules on your papers. Figure out what the IUPAC names are. This one. Okay, 2-methyl-2-propanol. How do you like that? 2-methyl-2-propanol. Okay, longest chain is 3 carbons long. 1, 2, 3. It's got an OH, so it's propanol. It's 2-propanol. And second carbon has methyl on it. So that is the IUPAC name of tertiary butyl alcohol. Okay, what about isopropyl alcohol? What's its IUPAC name? Two-propanol. Okay, so on your 3x5 cards, you should have on one side both of those names, and on the other side, those structures. All right? Because where do you need 3x5 cards? You need 3x5 cards for molecules that have a common name in addition to their IUPAC name. They have a common name, and they are very common organic compounds. You can go into a lab and you could look around for 2-methyl-2-propanol and never find it because the bottle is labeled T-butyl alcohol. All right? So that's why you kind of need to know some of these common names. You may never find a bottle of 2-propanol. You'll find it'll be labeled isopropyl alcohol or what? What's the other name for isopropyl alcohol? 2-propanol, and it's got another common name. Rubbing alcohol. Rubbing alcohol. All right? How many of you have a bottle of rubbing alcohol at home underneath your sink? All right? That's it. It's isopropanol. Isopropyl alcohol. Okay, I'll just flash through these. Methanol is toxic. It can cause blindness. Wood alcohol, back in the 1920s, the roaring 20s, everybody's getting a prohibition. They're just now getting used to alcohol. Some people are making their own alcohol. Some people drank wood alcohol and went blind. They thought, well, this is alcohol. It's methanol. It can kill you. A lot of times you go into a restaurant, a little thing they're burning, instead of having a candle, they got a little jar full of liquid with a wick coming out of it. Most often what's in there is methanol. Burns real nice and clean. So it can be used as a fuel. It's very combustible. Ethanol. This is the alcohol in alcoholic beverages. You ferment sugar, ferment various things, but predominantly sugar. You can convert it into ethanol. All right, we act like it is not, it's not toxic like methanol. Well, I wouldn't quite say that. I mean, if you went in and looked at things where alcohol is a risk factor for various kinds of things and cancers, it's there. It's there as a risk factor. So although we do drink it, it has its side effects and toxic nature. 2-propanol, isopropyl alcohol, secondary alcohol, disinfectant, astringent, industrial solvent. This is antifreeze, 1,2-ethane diol. So, I mean, if you put a hydrogen here, you have ethanol. You put another OH on ethanol, and you get ethylene glycol, or 1,2-ethane diol. You see how they're handling two alcohols? A diol, just like we would say a diene, a diol. This is antifreeze in your radiator, about 50% this and 50% water. It lowers the freezing point, it raises the boiling point. So in Texas, just running around with a radiator full of water is not a good idea. It's got a lower boiling point, and you can overheat your engine and blow your radiator cap So it's good to have antifreeze. You say, why do I need antifreeze in Texas? Well, you need it to lower the boiling point. This is toxic, extremely poisonous, and it is sweet. This tastes good. Don't taste it. But it has been inappropriately put into cough syrups and things like that in the United States 20, 30 years ago, more recently in other countries. It's cheap, and it kills. It will cause kidney failure. Ethanediol. All right, this is a molecule. I won't have you make a 3x5 card of this right now, but in chapter 17, when we get to triglycerides, this is the backbone of triglycerides, this glycerol. That's where you're getting the name, triglyceride. It is got a glycerol backbone. All right, I'm just showing you these molecules. Okay, let's get this under our belt, the classification of alcohols. In chapter 10, some of you noticed as you read chapter 10, it was going to classify carbons as primary, secondary, and tertiary carbons. And I said, let's kind of wrap our minds around that terminology when we get to chapter 12. And so here we are. So we want to learn what a primary, and we're going to abbreviate these as a primary, a secondary, and a tertiary alcohol is. You've already seen one tertiary alcohol, T-butyl alcohol. So a carbonyl that's a carbonyl. It's a carbon with an OH group on it. Carbonyl. We don't use that word a lot, but if you see it, you'll understand what it is. Okay. Methanol is neither. It's not a primary, secondary, tertiary. It's in a class all by itself. It's just a unique alcohol, one carbon with one OH, three hydrogens. That's methyl alcohol. But let's look at ethanol, 2-propanol, and this is T-butyl alcohol. All right, and so this is a primary, a secondary, a tertiary alcohol. And on the next slide, I think, or in a few slides here, I'm going to ask you to classify these alcohols. Just quickly go through and classify them. How do you classify them? A primary alcohol, look at the carbon with the OH on it and ask yourself how many carbons are attached to it. One. This is ethanol. Carbon with the OH has only one carbon on it. It's a primary. 2-propanol. Look at this carbon. It has the OH on it and ask how many carbons are attached to it. 1, 2. It's a secondary. This carbon, this OH group on it. And you ask yourself how many carbons are attached to that carbon. 1, 2, 3. Tertiary alcohol. Okay, so this 2-propanol, what is the common name of this 2-propanol? Isopropyl alcohol. That's isopropyl alcohol, ethanol, 2-methyl 2-propanol, or tertiary butyl alcohol. You can see the tertiary butyl alcohol, it's really picking up, this part of the name is coming not from the substituent, but that it is a tertiary alcohol. tertiary butyl alcohol. Oh well, this looks like it's answering the question for you. All right, I did. This was supposed to be a little bit harder. Okay, so classify these alcohols. What class is this in?
Two.
Okay, it is a secondary. This is a secondary alcohol. How about B? Okay, that is a tertiary alcohol. C. Primary? All right, this would be cyclobutanol. Cyclobutanol. So there's your carbon with your OH. How many carbons are attached to that? 2. So what is that? Louder? Secondary. Okay, so if we had like cyclohexanol, there's your carbon with your OH. What kind of alcohol is that? Secondary. There's a carbon here, and there's a carbon here. So, here's a stumper. Not a stumper, but let's do 1-methyl cyclohexanol. Let's classify that one. There's your 1-methyl cyclohexanol. Remember, every one of these carbons in cyclohexane has 2 bonds coming to it, so we could actually have a methyl group right there. What class of an alcohol would that be? How many carbons? Here is the carbon that has the OH. How many carbons are attached to that carbon? 3. 3. So that's a tertiary alcohol. So you have to look at the molecule and ask that question. How many carbons are attached to this carbon that's holding the OH group? Wow. Must have been. There's your homework. 2 sheets of paper. I must have had a kind streak that day. I don't know what it was. Okay, let's take a look at this. Okay, let's see. Let's just take a peek here. So for Wednesday, come here with problem 1, 2, and 3. Now, we haven't talked about reactions yet, but we have talked about that reaction in chapter 11. You see question 3? Draw the structure of the major product formed by the hydration of, what are you hydrating? Alkenes. So you know enough to figure this out from your chapter 11 so far. And in chapter 12, one of the questions will be, how can you make an alcohol? Well, one way to make an alcohol is through the hydration of an alkene. That's what you're doing right here, producing alcohols. And draw the major product. Okay, number 4, you are not prepared to do yet, or number 5. Number 6, you can certainly think about it. You actually probably are prepared to answer number 6. As we talked about solubility, you should at least start wrapping your mind around it. So, when we come on Wednesday, we're going to look at the dehydration of an alcohol. That's problem 4. And the oxidation of alcohols. That's problem 5. Okay? So if you want to read ahead and get familiar with those, you can. I'll give you time to do problems 4 and 5 in class on Wednesday, but we will finish it and collect it on Wednesday. I need your chapter 11. Everybody leave your chapter 11. Now, let's get all your names in the right pile. I'll take these away. And, just put your names back there, and I'll make sure I keep these separate.
Is the exam on Monday?
Pardon me?
Is the exam on this Monday?
Oh, the exam is next Monday. And here you go. Sign this one more time.